Okay, this is a continuation of the practice test for MAC 1140 pre-calculus. We're talking about the topics on Exam 1, Appendix 3, Appendix 4, and Sections 4.5 through 4.7. In the last video, we had gone up to number 32, where we were solving second degree and higher polynomial inequalities. And that entailed a discussion about cut points and test points in order to find the solutions. This same procedure is used when solving the type of problems that you're looking at right now on your practice test, numbers 33 through 35. These are rational means fractional, rational inequalities, and they also involve a discussion regarding cut points and test points. Okay, so this time we're just going to find the cut points in a different manner. When we were doing the problems in the previous video, like 30, 31, and 32, somewhere around there, we would have second degree or higher, and we would factor to get the cut points. We would look at what makes each factor 0. Here, it's what makes the numerator 0, what makes the denominator 0. That's what gets you the cut points. And then we're going to test the intervals based on the cut points. So, what makes the numerator, and let me write this more clearly, okay, the 0 for the numerator. Now, because the expressions in the numerator and the denominator are so simplistic, you can just look at them and tell what makes them 0. The number that you could plug in here to create a 0 would be 2. So that's one of your cut points. And the 0, and when the expression is more complicated, then you can just set it equal to 0 and solve it to figure out what the 0 is. But if it's just a linear expression like that, it's going to be real easy for you to figure out what the 0 is by observation. So -1 would be the 0 there, and as soon as you have those zeros, you have your cut points. Just arrange them on a number line. Don't put anything more than the cut points on your number line, or else you're going to create extra intervals that you don't need. Now test each of the intervals. 2 cut points will create 3 intervals. And you need to choose a number in each interval to test. So over here, I'm going to choose the number 2. That is part of this interval. In between -1 and 2, I'm going to test 0. And over here, I'm going to test 3. To represent the numbers to the right of 2. Each time you test any kind of a number, you're testing it in the original inequality. So here I go, testing -2. Okay, my original inequality is x minus 2 over x plus 1, and I am plugging in -2. That would give me -4 on the top, and it would give me a -1 on the bottom, which would be equivalent to just 4. And I'm trying to figure out, is this less than 0? No, it is not. So no to any of the numbers that are in the leftmost interval. Now looking at the middle interval, and I can just kind of, put this work anywhere. I'm going to squeeze it in here. I'm going to test 0 at this point. Okay, put it in the original inequality, so it would be 0 minus 2 in the numerator, 0 plus 1 in your denominator. So that's -2 over 1, which is equal to -2. I'm wanting to know, is this less than 0? Yes, it is. Any negative is less than 0. So yes for that. In the end of this problem, any interval that has a yes represents the interval solutions. Okay, I just have 3 left to test, so I'll do that right here. I'm going to test 3. So I'm going 3 minus 2 over 3 plus 1. Which is 1 over 4, and I'm wanting to know, is that less than 0? No, it is not. Okay, so in the end, final solution is all the numbers from -1 to 2, but not including those endpoints. You're not including the endpoints because there's no little equal sign, meaning that these specific numbers, if you were to plug them in right here, the -1 or the 2, you would get a number that's not less than 0. They wouldn't work. So you're signifying that by using parentheses rather than brackets. All these numbers in between here and here work. So that's just a picture of what works. But when you give your final answer where you're giving it an interval notation, then you have to go to pure interval notation. So you just give -1 to 2, meaning all numbers between -1 and 2, but not including those endpoints, are actual solutions. So there are infinite solutions between -1 and 2 because there's all those decimals that occur. Moving on to 34, it becomes slightly more difficult, and that is because rather than having a 0 over here, which is the way you must start these problems before you go looking for cut points, it has to be zeroed out on one side of the inequality. So we're going to zero it out by moving this 1 over here. That's the same thing when I show this arrow as subtracting 1, subtracting 1. But, I don't want you to get confused about where I'm putting this 1. So let me write it where I have more room. So this is x minus 7 over x plus 9 minus 1. And at that point, you have zeroed it out on the right-hand side. However, if you're going to combine a -1 with an x minus 7 over x plus 9, this needs to be a fraction. Furthermore, it needs to be a fraction that has the same denominator. Well, luckily, what makes this slightly easier than number 35 is that 1 can be named in any form or fashion as a fraction as long as the top and the bottom match. You can rename the number 1 2 over 2, 10 over 10, -5 over -5, x plus 3 over x plus 3. Anything you want as long as the top and the bottom match. Of course, we are directed into what we need by looking at this denominator and realizing I can't put two fractions together unless the denominators are the same. So we're going to call this one x plus 9 because it has to have the same denominator over x plus 9. That way I can combine it with the x minus 7 over x plus 9. At the moment that you get two fractions with the same denominator, in other words, renaming that 1, you can pull them together into one fraction. When you pull two fractions together that have the same denominator, you no longer change the denominator, just rename it. And then you put these together by way of the numerators. So you're going to have x minus 7 minus this entire quantity, and that would be a source of problem for some students because they forget to apply the negative to this 9. You're subtracting this entire quantity, which means you are subtracting, you're switching the sign on x, or subtracting x, same thing. You're subtracting 9 as well, which causes you to switch the sign on the 9. So it's really x minus 7. These stay the same, but these change with respect to sign. Then you can continue combining like terms. X minus x, that's gone. Negative 7 combined with negative 9 is negative 16. And then you have x plus 9 on the bottom. But at this point, you have taken what you had here, combined it into one fraction, and this is the fraction all simplified. So that's really what you're trying to solve. Okay, going back to the concept that the cut points are produced by looking at the numerator and the denominator. There is no cut point for the numerator. And that's because you can't make this 0. There's nothing you can plug in because there's no x expression in the numerator. However, there is a cut point for the denominator. The cut point for the denominator, which is really just the 0, is negative 9. So in this problem, rather than having 2 or more cut points, we just have 1. Okay, and that is just -9. Okay, so that means we only have two intervals to check. We have the interval to the left of -9, interval of numbers to the left, and the interval of numbers to the right. And we're looking for which interval, if it's either one of them, because sometimes it's no solution, might have solution numbers in them. So let's see, I'm going to test -10 right here to represent the numbers to the left. And then you can choose any number that happens before -9. I'm going to test 0. Okay, remember you're testing in the original inequality because, you just never know what kind of mistake you might have made when you started doing this. So always go back to your original inequality when using your test points. Okay, so it was x minus 7 over x plus 9. Right now I'm testing -10. So x, what you're testing, minus 7 at the top, and then x plus 9 at the bottom, -10 plus 9. I'm wanting to find out if that's less than 1. I think what I'll do right now is just continue moving to the right just to conserve space. So this is going to be -17 at the top, -1 at the bottom. That turns out to be positive 17. And positive 17, we're comparing this to being less than 1. And that, of course, is not less than 1. So no to the interval of numbers that are to the left of -9. They do not work. Now let's see if it's possible that the numbers to the right of -9 work. 0 represents those numbers. So now I'm testing 0. Okay, testing it in the original inequality, which was x minus 7 over x plus 9 is less than 1. So x minus 7 over x plus 9. Let's see, that turns out to be -7 over 9. Negative numbers, are they less than 1? Yes, they are. And every number is to the left, or what we consider less than 1. So we have yes right here, and then where you have the yes represents the interval of solutions. So if you were going to graph all the numbers that work, once again, this inequality does not have a partial equal sign, meaning that endpoint does not work. If you were to plug that in fact, it would destroy the denominator. It would make it undefined, and that's why it doesn't work. So if you were to draw this, you would just be saying, yes, the solutions start there, but that actual endpoint doesn't work. And then everything to the right, everything in this interval works. So there are infinite solutions there. They go on and on and on, which is why we need an interval to name them. When you're giving your final solution, interval notation is just -9 to infinity. So make sure you have good grasp of how to give your answers in interval notation when it's appropriate. Okay, so that takes us to 30 up through 34. Now we're going to do the hardest of these 3 problems that I offered you that have to do with rational inequalities. All right, so moving to number 35. Situated here. Stuff is all over the place. Okay, so it's x plus 8. Excuse the snoring in the background. It's my dog taking a nap, and he's very involved in his nap. Okay, so this is going to be x plus 8. Okay, so this turns out to be, a little bit more involved than what we did in 34. Those problems progressed with respect to difficulty level, numbers 33, 34, and 35. Because the last one was a 1, so once we brought it over here, real easy to rename it as a fraction with the same denominator. And this one's not much harder, just, maybe a little extra thought. So same thing. You need to zero it out on the right-hand side. So we're going to bring this over here. And when you bring it over here, it becomes a negative 9. So we're looking at x plus 8 over x plus 3 minus 9. And you can think of that 9, if you want to start thinking of it as a fraction, because it does need to be a fraction with the same denominator. Right now you can think of it as 9 over 1 once you brought it to the other side. Now, since the 9 is no longer on the right-hand side, that means we have effectively zeroed it out. Now, we want to make this fraction have the same denominator as that. Therefore, we have to multiply this denominator by whatever is required to give it this denominator here. So that means we're going to have to multiply by x plus 3, which forces us to multiply the top by x plus 3, because you can't just change the 9. It has to still be equivalent to 9. So when you're multiplying by x plus 3 over x plus 3, x plus 3 over x plus 3 is 1. And anytime you multiply something by 1, you're not changing its value, just its form, so that it's compatible with the operation that you're trying to accomplish. Okay, so now we have both denominators being x plus 3. So we can write it all as one fraction. Okay, the tops are x plus 8. And then be careful here. It's negative 9 times x. And negative 9 times 3. So now I've brought it into a single fraction. Clean up the numerator. This is going to be x minus 9x is negative 8x. And then 8 minus 27 is going to be negative 19 over x plus 3. Okay, now that you have a single fraction, you can go into finding those cut points. You may have to think a little bit harder on the at the numerator level. In the denominator, it's pretty obvious. So the cut points, which are really the zeros, the 0 of the numerator, well, that expression is a little bit more complicated, and that's because even though it is a linear expression, it has a coefficient. So maybe you won't be able to just tell by looking at it what the 0 is. So you can always take the expression if you want to know what zeroes this out and just set it equal to 0. And then that'll help you figure out what zeroes it out by solving it as a little equation. You could bring this over, and you would have negative 8x equal to 19, then divide by negative 8, divide by negative 8, and this is the value that zeroes it out. If you want to, whoops, put the negative in one spot. This negative you can put it wherever you want, bottom, side, top. Just going to put it up here at the top. So, if you want to know what this is as a decimal, just so you have a better grasp of where it's positioned on the number line, just put it in your calculator. 19, I think I have enough room there. 19 divided by 8, negative 19 divided by 8. Right there. I didn't put the negative in, but you just copy it now. So it's about 2.4, negative 2.4. Okay, just so you know how to arrange the numbers on the number line. Okay, the cut point for the 0 for the denominator. I have plenty of room right here, so I'll just write it. The 0 for the denominator, on the other hand, is very easy to just tell by observation. It's just negative 3. Okay, so now putting these numbers on a number line. You're putting -3 and -2.4. -3 would be further to the left, and then -2.4 would come before it. Okay, then you're going to choose test points in each interval. I'm going to test -4 to represent all the numbers in the leftmost interval. And then as you go from -2.4 to -3, there's -2.5, -2.6, -2. You can pick any of those. They're all they're all decimal. So I'm going to test -2.5. And then numbers that happen before or to the right of -2.4, 0 would be in there. So I'm going to test 0 to represent the rightmost interval. Okay, now the rest of the work is you plugging in each of these test values into the original inequality. So that original inequality was x plus 8 in the numerator, and x, and this is, I'm putting in -4 because I'm testing -4 right now. And then the denominator was x plus 3. Okay, that gives you, let's see, 4 at the top, positive 4 at the top, and then -1 at the bottom, which is -4, and we are testing whether or not this test value produces a value that is less than 9. This is just like the original inequality is looking for. So is that less than 9? Yes, it is. Any negative is less than a positive. Okay, so check that real quick. -4 plus 8 is 4. And then -4 plus 3 is -1, which was -4, and that is less than that. So we have yes for this interval. Now we're going to check the middle interval. So this time we're testing -2.5. That's -2.5 plus 8. And then on the bottom it's -2.5 plus 3. So -2.5 plus 8 would be 5.5. Just put that in your calculator if you want. And then -2.5 plus 3 would be 0.5. And then 5.5 divided by 0.5 is 11. And we are testing whether or not that's less than 9. No, it is not. So nothing in the middle interval works. Okay, then testing that last interval. This time we're testing 0. Original inequality is 0 plus 8, or x plus 8 on the top. We're using 0. And then 0 plus 3 on the bottom. That turns out to be 8/3. 8/3 is the same thing as 2 1/3, or you can get a decimal for it. It should be 2.333. And is this less than 9? This is approximately 2.3. And yes, it is. So 2.3 is less than 9. No, that's 2.6, sorry. It's 2 2/3, excuse that mistake. So it's approximately 2.7, but in any case, whether it's 2.3 or 2.7, that is less than 9. So yes, for right here, we have another interval of numbers that work. And we come again to a situation where the interval of numbers that do work, they're separated by an interval where the numbers don't work. So this is what we call disjointed solution set, and you have to talk about each interval, one interval at a time, joining them by the union symbol. So basically what you're going to say in mathematical symbols is that everything in the interval -3, again, there is no little equal sign. in this inequality, so you'll use soft parentheses on those endpoints. So we're going to say anything from here to here. This is called, you're going to negative infinity. That's what that interval is right there. It starts at -3 but doesn't include that endpoint, which is why there's a soft parenthesis, and it uses all numbers to the left of -3, which eventually get to negative infinity. So when you're giving your final solution, in interval notation, it's negative infinity to -3. Or you can also find solutions in the interval -2.4, which was just an approximation for -19/8. You want to use the actual numbers when you give your answers, not the decimal approximations. I mean, I talked about this being approximately equal to -2.4 just so you would know how to position these. So you want to use this actual number. So then you're talking about anything from -19/8 to positive infinity, because when you continuously go to the right, you're traveling to positive infinity. Again, that endpoint doesn't work because there's no little equal sign in the original inequality. So it's anything from 19/8 to infinity. This is a graph of what the solutions are. This is interval notation signifying what the solutions are. You'll be answering like that. You may be asked to graph it as well. Okay, so taking you up through 35. Now we transition to the topics in section 4.6, and that would be problems 36 through 41. Okay, so number 36 through 41, these are from section 4.6. Okay, so in number 36, it's asking you to list the potential rational zeros of the polynomial function. In other words, in fraction form, that's what rational means, list all the potential solutions, that's what zeros are, of the polynomial function. However, do not find the actual solutions. List the potential ones, but don't find the actual ones. Okay, so that's all we're doing to see if you can remember the theorem that was taught with respect to listing rational zeros. Okay, so 36, the function was 6x to the 4th plus 3x cubed minus 2x squared plus 2. Okay. Now, in order to list the potential rational zeros, this is where you get them from. Rational means they come in fraction form. So you're going to list all the positive and negative versions of these fractions that you're going to actually get by listing the factors of the constant. These factors of the constant will be the p-values. So in other words, the numerators of these potential rational zeros. And luckily this is a prime number, which means it only factors one way. So the top of these fractions that you're going to be coming up with, the p-values, they can either be 2 or 1. Then the q-values are found by considering the factors of the leading coefficient. So Q values are the factors of this leading coefficient. So whatever the highest power is in the problem, that's the leading coefficient. How can you factor 6? Being that it's not a prime number, it factors more than one way. You can factor a 6 like this, or you can factor a 6 like this. Okay, so that means your Q value can be one of 4 different values, and you have to list all of them. It can be a 1, it could be a 2, it could be a 3, it could be a 6. Okay, so here is our list of potential rational zeros. You go like this, stating what you're about to give. Put the plus or minus out here, meaning that the positive or negative version of each of the fractions that I'm about to create should be considered when you're looking for the solutions of the problem. This is a list of potential solutions, and they're all in rational form. Okay, so my p's can either be 1 or 2. The top can either be 1 or 2. I'm going to go with the 1s right now. So using 1 as the top, I have to pair that with each of the possibilities for the Q value, which is the denominator. So if 1 is the top, I could use 1 as the bottom. Again, using 1 as the top, I could use 2 as the bottom, or the denominator. Again, using 1 as the top, I could use 3 as the denominator. And again, using 1, I can use 6 as the denominator. That way, for this particular numerator, I have paired it with each of these potential denominators. Okay, so that gives me 4 different numbers, but actually 8 potential numbers that can be tried as solutions if you were going to start looking for the solutions, which it'll tell us to do in the next problem. Because you could say positive 1 or negative 1, positive 1/2 or negative 1/2. That's why we threw the positive and negative out front. That means the positive and negative version of each of these should be considered. Okay, now I'm done with the 1 as the numerator. Now I'm going to use 2 as the numerator. And we can clean up this list of values after we get done forming it. Like, in other words, if you see repeating values, once you start reducing them, then you just need to list that value one time. But for right now, let's just get them all listed. We can put them in order and clean it up and all that later. Okay, so now I'm using 2 as the numerator, and I want to pair it with each of these potential denominators. So it could be 2 over 1. 2 over 2. I keep using 2 as the numerator. I have paired it with the 1. I've paired it with the 2. It could be 2 over 3. And it could also be 2 over 6. Okay, now let's see. Okay, so we have a 1, a 1/2, a 1/3, a 1/6. Now let's make sure that none of these are repeating, which you can see that they are once you reduce this. This is a 1, and we've already mentioned the 1. 2/3, we don't have 2/3, so that one's okay. Here, 2 over 6, that's the same thing as 1/3, and that's already been mentioned right here. So the most cleaned up version of the list of potential zeros would be plus or minus and the following values. 1 over 1 is 1. 1/2 is 1/2. 1/3 is 1/3, so I gave all 3 of those. Let's see, what else? 1/3, that's already been mentioned. This has already been mentioned. I can mention 2/3. 1/6 was in the list. And you can try and put them in order if you'd like, but they're not going to mark it wrong because of that. 2/3, I mentioned the 2/3, so that's been done, and then there's this 2. Okay, so that is your list of potential zeros, and they come from just considering the factors of the constant, which plays the role of the numerator, over each of the possibilities for the denominator, which is the factors of the leading coefficient. Okay, moving to number 37. In 37, you're going to list these potential zeros, but then you're also going to find out which ones work, which ones are actual zeros. Potential just means there's a possibility that the numbers you're forming may be a solution. All the real solutions are definitely within the list, but not everything you try is going to work. And you can, employ the use of your calculator a little bit here as well to help you, get through the problem a little bit more quickly when we move on to 37 through 41. Okay, so here's 37. Okay, so 37 is f of x is equal to 4x cubed minus 11x squared minus 6x. And throughout this video, I'm just taking you all the way to the final answer and giving you every step that leads up to that solution. Please be very clear. Make yourself understand that you are writing an exam when you come into the college level, which means you need to be able to defend yourself. Explain why you got the answer, not this haphazard way of just, boom, let me throw an answer on there. I don't care if the problem is multiple choice or free response. I mean, free response, you have no choice. You must show everything, because the more you're missing with regard to your steps, the less points you'll get. And that's even if it's multiple choice. Okay, correct answer is only worth a few of the points. Most of your credit is going to come from how well you defend your answer or your solution. So you want to know how much work to show? Look at how much work I'm showing you. I might go a little bit over the top because I need to reach even the students that don't understand some of the more basic things. And so, I'll over-explain a little bit, but this is pretty much right on the money of what you need to be showing as well. Okay, so number 37, they give you this. Look at what the directions say. So you can see I'm using the same directions for 37 through 39. On the practice test. So it just says use the rational zeros theorem. That's what we just did, where we made those lists of potential zeros to find all the zeros of the polynomial function. So the way this works is you make the list, but we're going to go further with that list. We're going to try the numbers in the list until we find all of the real solutions. Meaning not imaginary solutions, because some of them will be imaginary. And then we're going to use these solutions, and let's get used to using the word zeros and solutions interchangeably. They mean the same thing. We're going to use the solutions to factor the original polynomial. Okay, so here we go. I'm going to demonstrate this 3 times, 37, 38, and 39. And you're going to see where I use the calculator just a little bit to get you started, so you don't have to go through a bunch of numbers in your rational zero list before you actually find the first one that works, because that would just be a waste of time. I do want you to show everything from start to finish, though. Okay, so here we go. Let's make the list first. So we're going to go plus or minus P over Q. Again, these are where the p's come from. So how can you factor a 9? Let's see, we could go 3 times 3, or we could go 1 times 9. These are your potential numerators. Okay, then these are the q values, which you can see play the role of the denominators. So they are the factors. You can either factor 4 as 4 times 1 or 2 times 2. Those are the things that you're allowed to use in your denominator. So here we go. It's all plus or, I'll just put the plus or minus once out here. That means that applies to each one of these. Okay, so let's use the smallest one here first, which is the 1. So 1 over so that's the numerator. So this is going to be 1 over, 1 over 1, 1 over 2, 1 over 4. Okay, so I want you to at least list these. You don't have to try each one, and we'll talk about that, how you use the calculator so that you're not trying each one. Okay, so I already did that one. Now let's consider the number 3. It appears twice, so just can do it one time. You don't need to do it twice. So it could be 3 over 1. That's a potential denominator. 3 over 2. 2 occurs twice. Just try do it once. Or 3 over 4. Okay, then let's see what's next. I can use this 9. I could do 9 paired with 1 as a denominator, 9 paired with 2, and I can pair 9 with 4. Okay, so those are all the potential solutions, and you know, some of them can be reduced like this. You could just call it a 3. This you could just call it a 9. Anything that you can reduce, you're welcome to do that as you list them. So now what they want you to do is find the solutions from this list, the real solutions. These are all real numbers. That's why they're called the list of rational zeros. Rational numbers are real numbers. So instead of trying each one of these, because, you know, if you're in a class where they're saying absolutely you can't use the calculator, we want you to show it. The way that you try each one of these is you try them through synthetic division. So I'm still going to have you demonstrate that you understand that the way to prove that it's a 0 without just looking at your calculator and that being the only skill that you have is to get the answer from the calculator, you know, that you want to be able to show that you know how to tie in all the concepts that we've learned in this section, in this chapter. And that means that you understand that when something truly is a solution, you should, when you try it in synthetic division, it should zero out. I mean, these are called zeros, so they should zero out when you use synthetic division. But why don't we use our calculator to get us started? And because for all you know, you could start by trying this number, 1, and not find an answer until you get all the way down here. And by that time, you've gone through many cycles of synthetic division. So right now we are at, let's see, a 4th degree, no, we're at a 3rd degree problem. This is 3rd degree. So you can get a couple of these answers right in your calculator, but I want you to, you're going to see how much work I show here so you can see what I'm looking for. Okay, first of all, let's get you to put this in here. We're going to put this in the graphing calculator for y is equal to and get the graph to be produced by the calculator, because where the graph hits the x-axis, in other words, the x-intercepts, those are also zeros. That's another name for solutions. They can be called zeros, they can be called solutions, they could be called x-intercepts with respect to graphing. So let's put this in. We're going to put 4x cubed. We just go to y is equal to on your calculator when you're going to graph. Clear out whatever's in there, and it's 4x. Right in this second column, you grab the x, the key that says xt theta n. Now put a cube on it. Raise it up to a power of 3. Next term was minus 11x, and you can hit this little square button in the first column if you'd like to put a square on it. So that one right there. Or you can go raise up to a power of 2, whatever you want. I'm going to just hit the little square button. Next term is negative 6x plus 9. Negative 6x plus 9. And press enter after you enter that last term. Graph it. And you know, you can fix this window. Under the zoom key right here, there is what we call a standard window. I would start with that. Okay, now, do you see how this is so narrow? It's so squashed together. That's because there's so many numbers on this x-axis. It goes from negative 10 to 10. So if you wanted to be able to see where it hits more clearly, give yourself less numbers on that x-axis. So instead of from negative 10 to 10, how about negative 5 to 5? That'll stretch it out and make everything more visible. You can do that under the key called window. These are pre-made windows. These are manual windows. So I'm going to go on my x-axis, -5 to 5. X min would be the -5. X max would be the 5. And now I'm going to graph it again. Okay, now there's a clearer view of what the x-intercepts are. Like it looks like it hits at -1. That's some kind of fractional number. It also looks like it hits at 3. So you're cheating a little bit when you do this, but you can still show quite a bit of work while employing what your calculator's telling you. Okay, so I'm going to start with -1, and I'm going to verify, I'm going to show that it actually is a 0. Okay, so I think -1 is a 0. Put it in here. If it truly is a 0, it's going to zero out when you do synthetic division. So let's recall how to do that. Now the reason I'm not switching it is because when you're getting an x-intercept right from the graph, it's not a number that's attached to an expression that contains x. That's when we switched it before delivering it to this box. But if you're getting it from a graph as an x-intercept, use it as is. Okay, then the numbers that are in the polynomial are 6 for the 4th degree term, 3 is the coefficient of the 3rd degree term, -2 is the coefficient of the 2nd degree term, and then that's the constant. Leave room here. Okay, I'm looking for it to zero out in order to verify that this -1 truly is a 0. So we're going to find that out right now. Drop that down. -1 times 6 is -6. Combine these, you get -3. -1 times -3 is 3. Combine these, and you get 1. -1 times 1. Okay, so this is 6. Make sure I copied this right. Nope, I did not. This is what I actually did. I actually copied the numbers from number 36. So let's start that again. Sorry about that. I was looking at the problem above it. I accidentally grabbed those numbers. So the problem that I'm working on is this one. So 4. Let me see what I even entered in here. Yep, I did enter the right numbers for the graph, but then I grabbed the wrong ones when I did synthetic. So it's 4, -11, -6, and 9. I put this under here. 4, -11, none of these powers are skipped, so I don't have to put a 0 in there anywhere. And now let's check out whether it's going to zero out or not. So we have 4 here. -1 times 4 is -4. Add these up and we get -15. Then -1 times -15 is 15. Add these up right here, just as I'm adding up any column, is 9. And then -1 times 9 is -9. And that zeroes out. Okay, so yes, -1 is considered a 0, or what we consider a solution. In a graph, it is signified by an x-intercept, as I just demonstrated on the calculator. So this is what happens. Once you find a number that zeroes out in the synthetic division process, you have brought this down a degree. So now you're at 2nd degree. If you want to go further with this, you could try another 0 that you may have seen on the graph. You can bring it down to 1st degree even. So you could go like this. You could look at this graph again. It looked like it went through -1, and we just verified that that truly was a 0. This also looks like it goes through 1, 2, through 3. So if we want to bring it down from 2nd degree to 1st degree so that we can just solve for that remaining 0 ourselves, we can just continue the synthetic process right here. So first we synthetically divided -1 into the original. This is what's left at this point, rather than 4x cubed minus 11x squared minus 6x plus 9. Now it's 4x squared minus 15x plus 9. And we think that 3 is another 0, according to the graph. So let's see if it really is. Drop down that first 4. 3 times 4, 12. Add these up. This plus this, negative 3. 3 times negative 3, negative 9. And yes, we are zeroing out again. Okay, so yes, 3 is also a 0. And these zeros help us factor, because part of the instructions is that you should be able to use these zeros to help you factor the original function. Okay, now you are at first degree. Every time you make a synthetic division pass through the problem, you bring it down a degree. So now we're at this was third degree when we started. This was the original problem. Then we knocked it down to second degree on that first term. Now we knocked it down to first degree. So this would be 4x. If this is first degree, this is 1 degree less than that. So that's what you have left over underneath this bar. 4x minus 3 is equal to 0. Now let's, review with you some background theory on the number of solutions for any kind of a graph. Well, you could see right here that this graph touches the x-axis, and the x-axis is nothing but real numbers. So everywhere that a graph touches the x-axis, those are the solutions. But you're going to show some of it by algebra. We verified that -1 and 3 are indeed x-intercepts, therefore they are considered zeros or solutions, whatever you want to call them. And now we're going to get this answer, telling you exactly what it is. So, because it's fractional, you have to go and get it from this equation, first degree equation that remained. Bring this over here, and it's 4x is equal to 3. Divide by 4. So that other solution that you were seeing that occurred right before 1 on the graph, that solution right there is 3/4. As far as factoring this thing, you're going to use the zeros that you discovered as you worked this problem. And in factored form, they assume the opposite sign as the sign that they have when you're just talking about them as a solution. So yes, I could discuss the fact that -1 is a solution, or 0, whichever term you want to use, but this is how it looks in factored form. It assumes the opposite sign. Factored form, 1 sign, opposite sign when you're talking about it as a 0. Okay, another thing that was a 0 was the number +3, so therefore it appears as -3 when it's being written as part of a factor. And then the other factor that remained was this. This was the last factor that was left over after we had brought it all the way down to first degree. So doing everything that this problem has asked us, use the rational zeros theorem to come up with these rational zeros, and then from that list find out which ones are the actual solutions. Notice that these solutions that we found, -1 and 3 and also 3/4, notice that all of those are in this list of potential solutions, potential zeros. See, the -1, you're to consider the positive or negative. So here's the 1, the 3 was in there, and 3/4 was in there. But again, instead of going through this whole list, I helped you whittle away some of that work just by using our calculator in the middle of the problem. So we would know like where to start in the list and make some wise choices that will cut down on the work. Okay, so you can see from these choices right here that our answers were what, 1, 3, and 3/4. or was it? Yeah, -1. So there can't be this 4/3 thing, so it has to be this steep. Okay, -1, 3/4, also 3, and then here it is in factored form. Notice that these factors assume the opposite sign on the 3 and the -1, and this was the factor that was left over underneath that synthetic division bar. Okay, moving on to 38. Okay, here's problem 38. So we have f of x, 3x to the 4th minus 5x cubed plus 8x squared minus 10x plus 4. Okay, so same set of directions here. We're going to list the potential rational zeros. Okay, remember the p's come from this constant. They are the factors. So 4 can be factored as 4 times 1 or 2 times 2. These will play the role of the numerators in these fractions that you're going to come up with. Then this is where you get the q values, in other words, the denominators. The 3 only factors as 1 times 3, so you have only 2 possibilities for what your denominator can be. So let's start making the fractions. Using 1 as the numerator, we compare that with the 1. We compare it with the 3. Okay, so we're done with the 1. Now using the 2 as the numerator, we compare it with 1. We compare it with 3. Now using the, we don't need to do that again. Now using the 4 as the numerator, we compare it with 1. We compare it with 3. So this shows that you know how to use the rational zero theorem. Okay, then you're going to see which one of these works. And every time you find one that zeroes out the polynomial after using synthetic division, you're going to be bringing it down a degree. And you can bring it all the way down to first degree if you like, if the graph even offers that many solutions, because it's not going to offer imaginary solutions. It only offers real solutions. So sometimes you can only bring it down to second degree, and then you need to know how to factor. So let's try and see what we can get in here from the graphing calculator. Clear out the other one and start pressing in this polynomial. It's 3x raised to the 4th. Okay, then it's minus 5x raised to the 3rd power. Then it's, let's see, plus 8x squared. Then it's minus 10x. And then it's plus 4. Okay, and then we can try a standard window, which I believe it might already be on. Now, I think I changed the window. I'm just going to start off with a standard window. Yeah, way too many numbers on that x-axis. Let's just get a clearer picture here. We could even go -3 to 3 to give ourselves a nice clear view of this graph. Okay, so it looks like the only number that this hits on is positive 1. And I'm going to go a little bit further on that window. I'm going to go -5 to 5 because I think because it's so stretched out, it's distorting it a little bit. Okay, so it looks like this is a touching point on a graph, which means something in algebra. Whenever you have a graph that only grazes the x-axis, it just touches it and then bounces right off it, so sometimes they're called bounce points. That indicates that there is a multiplicity. In other words, that solution actually occurs twice. in the whole, in the grand, the grand finale of everything. That's what we refer to as a multiplicity, when the graph bounces off a particular x-intercept, which appears to be positive 1, but let's verify it algebraically. So we're going to go 1, and you can prove it to yourself algebraically that that solution works twice. Okay, the only way you would do this is if you see that the graph bounces or touches, both of those words are used in math books to signify a solution that has multiplicity, that occurs 2 or more times. When the graph bounces off a specific x-intercept, that indicates to do what I am doing right now. Okay, so it appears that we have multiplicity occurring at the value positive 1. Okay, let's figure out if it works as a solution. So 3 for my 4th degree term, negative 5 for my 3rd degree term, 8 for my 2nd degree term, negative 10 for my 1st degree term, and 4 for my constant. Bring down that 3. 1 times 3 is 3. Add these up, you get negative 2. 1 times negative 2 is negative 2. Add these up, you get 6. 1 times 6 is 6. Add these up, you get negative 4. 1 times that, there we go. It has zeroed out already. So we already know that 1 is a solution, or a 0. But because it's a bounce point, it should work more than once. So we have, now remember, to be clear about this, we started off at 4th degree. By the time you got right here to this next string of numbers underneath the bar, you're at 3rd degree. You've brought it down a whole degree when it zeroes out like this. So this would be 3x to the 3rd degree, negative 2x to the 2nd. This would be the x to the 1st degree term. This would be the constant. We want to see if positive 1 works yet again. And we're going to try it on this reduced degree polynomial. So bring this down, the 3. 1 times 3 is 3. Add these up, you get 1. 3 plus negative 2 is 1. 1 times 1 is 1. Add these up, you get 7. 1 times 7 is 7. Add these up, you get 3. 1 times 3 is 3. Add these up, you get 3. All right, so that did not zero out again. Let me check this out. And 37. Okay, hold on 1 second. Okay. All right, so I went and tried this one to see if it worked again, because this looked like a bounce point that and when it's a true bounce point, when it really does touch this. However, what I am finding out right now by the algebra that I'm doing is that maybe it does dip right below. And the graphing calculator can be deceiving in some respects, because you can't really tell how far that dips below it. Even if I was to make the window a little bit clearer by putting less numbers on it, It looks like it's somewhat underneath it, which means it comes through it and then up through it again. So what I did just now by doing this algebra is I just verified that that is not a bounce point. So the algebra, not the graph, because again, the graph can really help you to cut down on your work, but sometimes, you know, you're not sure if it's just looking distorted, you're not sure of what you're seeing, so you have to be able to try it algebraically. Now, if it truly was a bounce point at the number 1, then I would have been able to use the 1 as a solution more than one time. But look what happened here. So negative 4 plus 7 is 3. And even if I was to go further, you can see that it's not zeroed out. That's not a 0. So that 1 is not a multiple solution. Let me write that. 1 is not a solution that has multiplicity. It's not a solution with multiplicity. Doesn't occur more than once. Multiplicity is just the word for that. So this is what we're going to do. We found out that the very first time it did zero out. Let me get my losing things here. Oh, there it is. It did zero out the very first time that I used this one. It did work. So why don't we go back to what was left over at that point, because I think that's all that we're going to get from here. I mean, you can see on this graph that you really can't tell what else it goes through. We knew that it might have potentially gone through 1, and that might have potentially been a 0, and then we verified that it actually was. So this is what was left after that. I mean, I did go and try it again, but it didn't zero out. So we have to go back to what we had in the step before it, realize that it's 3rd degree, and come down here and work on it algebraically. When you can't go any further with the synthetic division, then it's time to break off into the factoring. Okay, so let's see. This is 3rd degree, so that's 3x to the 3rd degree minus 2x squared plus 6x minus 4. So how can we get the remaining zeros from what we have left here? Well, we can say what makes this 0, so that we can find the remaining zeros another way other than using the graphing calculator and synthetic division. Graphing calculator gave us as much as it could. We knew something was going on at 1, and then we verified it. However, when it looked like it might have been what we call a bounce point, which signifies that there might be potential multiplicity there. In other words, that the solution could actually work again. But by algebra, we verified that that wasn't the case, because it did not zero out when I tried to use it again. So I went back up to what was left after I had tried the value 1 the first time. We were at 3rd degree. This is that 3rd degree expression, and I'm going to factor my way to the rest of the solutions. Since you can't go any further with synthetic division, and the calculator won't give you anything further because it doesn't have any other x-intercepts. Okay, this is 4 terms, so we can do factor. We can try factor by grouping. Okay, so let's see, what can we do here? Hopefully this will factor by grouping. We can take out x squared here, and then we'd be left with 3x. X squared times 3x is 3x cubed minus 2. X squared times negative 2 is negative 2x squared. Then we can come back here and factor out what is common to these two terms, and that would be 2. That leaves us also with 3x minus 2, so perfect. This times this is 6x, this times this is -4, and we're on our way to finding the rest of the zeros by factoring. Now look at this entire expression as two terms. They both have the common element 3x minus 2. So take that out. And then what's left over is x squared plus 2. Okay, so I already know that 1 is a 0. And I'm about to find another one. Altogether, there are 4 solutions, but they might not necessarily all be real numbers. Your directions asked you for only the real solution. So I can take this 3x minus 2. If you want to know what solutions are, you can just look at what zeroes out any of these factors. Is there a real number that will zero this out? And you can do that by just setting the factor equal to 0 and then solving it as an equation. So you can bring this over here and then divide by 3, divide by 3. And you have x is equal to 2/3. So now I have another solution. This is also a 0. Okay, so I'm up to 2 answers. However, this is 4th degree. This original problem was 4th degree. So what about the other 2 solutions? Are they real? Well, look at your factored polynomial, what you have left at this point. You factored it. We worked with one of the factors and got this, but if we were to try and work with the other factor, what happens? We want to know what are the zeros for that particular factor. I don't know if you see what's happening here, but as soon as you bring the 2 to the other side, it's -2. And this is where imaginary numbers come from. Yes, you would be able to bring this to x. You would report both the positive and negative root. And if these were real numbers, that would be good. You could actually offer them as solutions. But the whole definition of the term called I, imaginary term called I, is it's a -1, and this -2 is -1 times 2. So you could leave the 2 underneath it, but the negative comes out as an I, and we're just not looking for solutions like that. Your instructions said find only the real solution. So we cannot offer this as a solution. However, we found as many real solutions as we possibly could, and that was the 1 that we found here, and the 2/3 that we found here. But we can finish the last part of the problem, which is to offer the function in factored form. Okay, so here we go. Factor the original function. So it's f of x. We can use the zeros that we found and go x minus whatever the 0 is. The minus meaning that you're going to switch the sign on the actual solution. So +1 was a solution. Right here, it appears as a -1 when it's in factored form. And then we also had 2/3, but they don't like you to give fractions as part of your factors. So you're going to go back to where this came from. You got this solution from the factor 3x minus 2. So it's 3x minus 2 for one of the factors. And then the other factor, which we discovered only offered imaginary solutions, is the x squared plus 2. So there it is, all in factored form. Okay, and let's see what kind of answers there were for this one. So we said 1 and 2/3 were the only actual real solutions. This is problem number 38. And yes, that was A. So 1 and 2/3 we found, and then here is our factored form of the solution for number 38. Okay, that's a tough one. Okay, moving to number 39. And in problem number 39, let's see, what do we have here? Okay, in problem 39, we have f of x is equal to 2x to the fourth minus 20x cubed plus 51x squared minus 10x plus 25. Okay. All right, so first thing we're going to do is give our list of potential solutions, both in their positive and negative form. And our final solution will be in this list. Only we're not going to go through the whole list. We're going to get our calculator to help us out with the first, couple to bring us down to at least second degree and potentially even first degree. Okay, so let's see. Remember that the p values come from down here and the q values come from down here, and they are in fact the factors. So 5 times 5 is a way to factor 25, and 1 times 25. So the numbers 1, 5, or 25 can play the role of the numerator. This is a prime number. It only factors as 2 times 1. The q's are the denominators. Okay, so now we're going to make our list of p over q values. I already put the plus or minus out here instead of doing it each time we create a fraction. Okay, so these are the numerators. I'm going to go with the 1 first. I can pair up the 1 with this 1. I can pair up the 1 with the 2. Okay, so I've exhausted all possibilities there with 1 as the numerator. Now I'm going to go to 5, and you don't need to do it twice. So I can pair up the 5 with the 1. I can pair up the 5 with the 2, exhausted all possibilities for 5. Now I'm going to go with 25 as the numerator, 1 as the denominator, and I can also try 2 as the denominator. So anything that is a solution is found in this list. All right, so now I'm going to put it in the calculator because instead of trying each one, like I said, you could start with number 1 and work your way down the list. You could try positive 1 and negative 1 in synthetic division, seeing if those zero out, but it might not. This might not zero out. It might not happen until down there. So to cut down on that work, we're going to get the calculator to tell us what some of the zeros are, but still use them to show the work. We'll verify that they truly are solutions by synthetic division. So we're going to feed in for y is equal to 2x raised to the 4th power minus 20x raised to the 3rd power plus 51x to the 2nd degree minus 10x plus 25. Okay? Then I'm going to use a standard window just to start with. Okay, really scrunched in, so I'm going to give myself way less values here. I'm going to try negative 1 to maybe, let's see, what is this? 1, 2, 3, 4, 5, 6, and maybe like negative 1 to 6, just so it's not so scrunched in. Whoops, no, I'm going to go window. So negative 1. Now we can see it a little bit more clearly. That does look like a bounce point, but again, we need to verify this. I see that it touches at 1, 2, 3, 4, 5. So we're definitely going to try the one and only solution that this graph seems to be giving us. But because, I'm going to stress again, when your graph bounces off or looks like it bounces off a particular x value, that means that that x-intercept, that solution, may occur multiple times. It has a multiplicity of an even multiplicity, so at least twice. So let's see if it truly is a bounce point. So there seems to be a bounce point at 5. Also can be called a touching point. a bounce point at x equal to 5. Therefore, the value x equal to 5 has multiplicity. In other words, it can occur as a solution 2 or more times, an even number of times, as a multiplicity. Anything that's a multiplicity has a multiplicity, an even multiplicity. I should write it like that. Value x equal to 5 has even multiplicity. Well, the first even multiplicity would be 2, so it occurs at least twice. If that truly is a bounce point. Same thing I was trying to explain in number 38. It looked like my graph had a bounce point at a particular value, but then when I tried it algebraically, it turned out that it wasn't a bounce point. It wasn't a point where the graph just touches the x-axis and then bounces off of it. So I'm going to try right now to see if this 5 has even multiplicity of at least 2. All right, so we have x to the 4th. This is our third degree coefficient. This is our second degree coefficient. This is our first degree coefficient. And this is our constant. Okay, bring this down. We have 2. 2 times 5 is 10. This plus this is negative 10. This times this is negative 50. This plus this is 1. 1 times 5 is 5. Add this up and you get negative 5. Negative is negative 25. This is 0. Okay, so we've already proven to ourselves that this is a solution one time. We are now down to third degree with this string of values that we have underneath the bar. Let's see if 5 works yet again, thus verifying that it has an even multiplicity. In other words, that it occurs at least twice. I mean, it could occur also 4 times. But we're going to see what happens here. We're going to bring this down to second degree now. So second degree, if it zeroes out again, bring down the 2. 5 times 2 is 10. Add these up, you get a 0. 5 times 0 is 0. Add these up, you get a 1. 5 times 1 is 5. Add these up, you get a 0. And then 0, yes, it does zero out again. So the 0 called 5 occurs twice. So when you go to factor it, it's going to be x minus 5 times x minus 5. It actually occurs twice, therefore it will appear in 2 different factors. Now, what do you have left at this point? Well, now you're down to second degree, and there isn't much left here, nor does it look like 5 is going to occur. Look what's left here. This is your second degree term. There is no first degree term, and this is a constant. So what remains right here, what is suggested by these string of numbers is that 2 plays the role of your second degree term. There is no first degree term. And then what comes after the first degree term is the constant. This is all you have left. And I can tell by this that the other 2 solutions are in fact not even real. They're imaginary, because the minute that you bring this over here, anything squared that's equal to a negative means that you're going to get imaginary solutions. Because even if you did take this further, it would be divided by 2, divided by 2. You'd have x squared is equal to negative 1/2. And then when you go to take the square root here so that you can get solutions for x, you're taking the square root of a negative number. This part comes out as an I, and you would be, the solutions you would get here would be plus or minus I times square root of 1/2. And of course you could even You could simplify that even further, but let's not bother because we're not supposed to be giving imaginary solutions. Directions only asked for real solutions. So the solutions that we have at this point is we know that the number 5 occurs twice, and what we had left over at this point right underneath this bar is this particular expression. And that particular expression can't be factored. You cannot factor the sum of, two squares like this. So you just can't factor that. And in fact, we found that those were imaginary solutions. So now we are ready to give our factored answer. Okay, the only two zeros for this particular problem, you're going to say 5 with a multiplicity. That means how many times does it occur as a solution? With a multiplicity of 2. And then when you go to factor it, it's going to look like this. That positive 5 appears as a negative 5 in a factor, but it occurred twice. And then the remaining factor, after it occurred twice, was 2x squared plus 1. So there it is in factored form. Okay, let's see what kind of solutions there are for 39. For 39, let's see. No, it's just 5. It's not negative 5. It's 5 occurs, positive 5 worked twice. That's what multiplicity means. Occurs twice, and then this was the factored form of the answer, because that x minus 5 times x minus 5, and then that this was the polynomial that was left after you used the 5 twice in synthetic division. So that 2x squared plus 1 is right there, and of course this can be written as, and they want you to write it like that, as x plus 5 squared times 2x squared plus 1 when you give your final factored version of the function. Okay, so those are, as you can see, a ton of work, but you're cutting down on some of the work by using the calculator. Okay, now we go to numbers 40 and 41. Those are pretty quick problems, and they talk about the intermediate value theorem. And these problems, once again, that I am working on, numbers 36 through 41, are from section 4.6. So like I said, it says that at the top of the practice test. I sectioned them off for you so you can tell where to go to look for examples. Okay, I'm on number 40. So what the intermediate value theorem says is that you're going to use each endpoint So they're going to give you an interval, and they'll have an endpoint here and an endpoint here. So this is the shortest way I can think to write it. You're going to take the function and plug in one of the endpoints, and let's say you get a positive value. And when you go to plug in the other endpoint, you get a negative value. And it doesn't matter which one comes out positive, which one comes out negative. My whole point is if these come out to be opposite in sign, once you evaluate the function at each of these endpoints, if they're opposite in sign, that implies that yes, there is a solution, or what we call a zero. Solution means zero, between which is the same thing as saying this. There is a zero in the interval mentioned. In this case, I just called it A to B. Okay, that is the intermediate value theorem. So here we go, using it. In number 40, you are given f of x is equal to 5x cubed plus 5x squared minus 3x plus 3. And you are going to check out the endpoints between -2 and -1. Okay, let me make sure that I copied it right. 5x cubed, 5x squared, -3x, +3. Okay, so first I'm going to evaluate at this endpoint. So 5 times -2 cubed plus 5x squared minus 3x plus 3. Okay, so this is going to be -8 times 5. So that's -40, and you can put it all in your calculator if you want. This will be 4. 4 times 5, which is 20. This will be 6. -3 times -2, and this will be 3. Okay, so these put together is -20 plus 6. Let's put it all in your calculator if you want. -14 plus 3 is -11. So that was one of the values I got for that, -11. And then, let's see, now I'm going to do the other one, which is the other endpoint is, let me write this right here. So when I evaluated at -2, it was -11. And now I'm going to do the work for the other endpoint. The other endpoint is -1. So it's 5x cubed plus 5x squared minus 3 times x plus 3. Okay, this would be -1 times 5, which is -5. This would be 1 times 5, which is just 5. This would be -3 times -1, +3, plus this extra 3 at the end. These cancel each other out, leaving you with 6. So when you go the function evaluated at -1, you get a 6. Okay, so notice that after evaluating at each of these endpoints, one is negative and the other one is positive. And as long as that is how it turns out, that means yes, there is a solution, or what we call a 0, in the interval given. There does exist a solution somewhere between -2 and -1 for this particular polynomial. Okay, finishing off this batch of problems from section 4.6 with number 41. Okay, 41, just another opportunity for you to try this intermediate value theorem. All right, so now we're checking this. Let's see. I think I copied this wrong. Let's see. I did. Sorry. Looking at a problem right above me. I'm looking at another problem on the practice test. Sorry about that. Okay, so 41 was really 3x cubed plus 2x squared minus 5x minus 8. and we are going to check it in the interval 1 to 2. Okay, 3 to -5, -8. Okay, so the function evaluated at 1, I'll do this endpoint first, is equal to 3 times 1 cubed plus 2 times 1 squared minus 5 times 1 minus 8. So that's going to be 1 cubed is 1 times 3 is 3. That's 1 times 2, so that's plus 2. Minus 5 minus 8. You can put it in your calculator if you like, these numbers right here. So this would be 3 plus 2 is 5, take away 5. I'm not even going to bother to put in the calculator, it's just -8. Okay, so when we evaluated at 1, we got a negative value. On the other hand, now trying the other endpoint, which is a 2, it's 3 times 2 cubed plus 2 times 2 squared minus 5 times 2 minus 8, plugging that 2 into the original inequality. Okay, so this is 8 times 3, 24. This is 4 times 2, 8. This is 5 times 2, 10, but negative. And this is -8. So we have 32 minus 10 minus 8. And that is 14. So when we took the function and evaluated at the other endpoint, we got positive 14. Okay, once again, in this problem, notice that at one endpoint you got a negative, and the other endpoint you got a positive. So yes, the question is, for these two problems, 40 and 41, is there a solution somewhere in between these numbers, somewhere within this interval? So yes, there is a 0 in the interval 1 to 2. Okay, let's check both of those answers. Yes, both of those were yes, that there is a solution in the interval. Okay, that takes us all the way through 41. In the last video, I'll be doing 42 through the end of the review, which is 48.